Hello, chemists. It's Mr. Gopal here with a very important lesson on redox reactions. All right. So this is in Unit 9, which is oxidation and reduction. All right. I'm going to quickly define some terms. After we talked about the focus question, we want to identify and balance half reactions and redox reactions. I'm going to focus a little bit more on the balancing aspect. All right. So one reason why this is important is that we can create battery situations using oxidation and reduction principles, all right, which is part of what we're seeing here. This is not a battery per se, but we're able to conduct electricity across different solutions using what we call a salt bridge. More on that in another video. Now, if we go down, we see a very kind of complicated half reaction, all right? And I want to break this down actually with a simpler example. So they have this written out for you. It's a pretty good one. What I'm going to do is I'm going to analyze and identify oxidation and reaction and talk about the balancing process with an equation that's a little bit simpler. Okay, so I'm going to share a whiteboard. Now, let's consider the following equation. I'm going to define oxidation and reduction, and then I'm going to talk about how to balance this, how it's related to the amount of electrons that you have, as well as the other principles of balancing equations that we've already looked at. So we have just one moment. We have CO. That's cobalt in an aqueous solution. So cobalt is a metal. We have another metal, nickel. That's in a solid state. And now we have the same elements afterwards. However, as you can see, the charges are different. And this change in nickel's charge, let me redraw that. This change in nickel's charge, it happens as it's transitioned into the aqueous solution. Okay, and so if I'm saying oxidation, what I mean in that point is an increase in charge. That increase is brought about by the loss of electrons. Hopefully this makes it obvious that when I say reduction, I'm talking about a lowering in charge or a reduction in charge. It's a good way to remember it. It's in the name. And then it happens through the gaining of electrons, all right? Okay, so we remove electrons, our charge increases. We add electrons, our charge decreases. That's the first thing. Now, this is unbalanced with respect to charge. We may have the same amount of moles of each element on left and right. However, we don't have the same net charge. The net charge, I'm going to start with the net charge of nickel. 0 over here, or sorry, I'm going to start with the charge of nickel on left and right. It's 0 over here. It is +2 over here, as they say. Okay, and then cobalt is +3 here, and it is +2 over here. If I add 2 and 2 over here, that means that I get a net charge on the right-hand side, the product side, of +4. If if I add 3 and 0 here, I have a net charge of +3. And so this leads me to my principle of balancing redox equations, or redox reactions. Balance to balance redox reactions, need the same net charge on the reactant and product side of our equation. All right, that is our first principle. And so I'm going to start off by talking about where we place electrons based on whether we're talking about the oxidation half reaction or the reduction half reaction. So I'm going to start with the oxidation one, and that is our nickel. And so when we talk about that one, we add our electrons on the product side. So I'm just writing this half of the overall total reaction. And since I know that this nickel on the left-hand side, this solid nickel is neutral, I have to add 2 electrons to the right-hand side in order to make the other side neutral, okay? So with oxidation, I balance the right-hand side by adding electrons there. I'm just gonna write that here. For oxidation reactions, add electrons to the right-hand side of the half reaction. This is not the way. Okay, and then as you might predict for the reduction, I'm just going to write the cobalt part from above. For this one, I balance by adding electrons on the left-hand side. So I'm always adding them to the side where the charge is greater. I'm just going to move that arrow over a little bit to make space. And if I have 3 plus on the left-hand side, I have 2 plus on the right-hand side, I have to add 1 electron over here, okay? And so now if I combine these, what's going to happen is I'll have nickel plus, CO 3 plus the solid nickel that's neutral plus 1 electron is equal to nickel 2 plus cobalt 2 plus 2 electrons. And my net charge on both sides is still not quite equal. I have 1 more electron, 1 more stray electron on the right-hand side than the left-hand side. That means that I have to take this I have to take this redox reaction and double its size in order to ensure that I have the same amount of stray electrons added to both sides. So that's going to look like 2 CO 3 plus. I'm going to stop writing the AQ, plus 2 electrons is equal to 2 CO 2 plus. There we go. Okay, and now when I put it all together, here's my overall equation. That is going to be 2 CO 3 plus Ni equal to Ni 2 plus 2 CO 2 plus. And now here's the beautiful thing. The 2 electrons on left and right have canceled out. But now because of this new balancing, based on what I discovered from taking the oxidation half reaction and balancing it, in taking the reduction half reaction and balancing it is that I can see that I have the same net charge on left and right. Let's walk through it. I have this cobalt that has a charge of 3 plus, but I have 2 moles of that. So overall, I have 6 plus over here. Okay, so that's 6 and 0, right? Because that's still neutral. Here I still have a 2, but now I take 2 multiplied by my 2 plus, and I have a 4. Okay, so 2 plus 4 equals 6. 6 plus 0 equals 6. And I have balance on left and right. So that is my new balanced equation. So we've seen some similarities to previous balancing strategies, right? That is that I need to have the same amount of moles of all the elements on left and right. The new strategy is that I pull out individual elements from left and right, and I figure out if they're being oxidized or reduced in this, and then I add electrons to the appropriate side. If they're being oxidized, that means that there is a raise in charge, okay, and I have to add electrons to the product side. If they're being reduced, that means there's a lowering in charge, and I have to add electrons to the reactant side. Finally, I have to make sure that the amount of electrons I've added to both sides balances out, and I might have to multiply one or other half reactions, or maybe even both, in order to make that happen. Now when I combine them, the electrons that I've added on left and right cancel out, and the overall net charge on the reactant side should match the overall net charge on the product side. So there you have it. I would take a screenshot of this, and I hope this kind of deliberate walking through of what a redox reaction is and how to figure out how to balance it was helpful to you. That's all for this time, but we will take a further look at this because this is a tough unit. Stick with it, and I will see you soon.